All right, here we are with a standing wave problem. We are given this problem the length of a string that's fixed, and we're given the string's linear mass density as well. And then we're told that the string can be observed in two particular resonant frequencies, just two random ones. They're giving us 400 hertz and 480 hertz. And then there's this important note after that. There are no resonant frequencies between these two. So those two frequencies are consecutive frequencies on a string. Okay, so one of the things we can know about a fixed string is that the different resonant frequencies are all multiples of, let's think about it, they're all multiples of the fundamental, right? So I'm just going to pause for a moment and take you through that real quick. So say I consider the fundamental frequency. Draw these out. If you're having any trouble at all with standing waves, that might be because you're not drawing them out. So here would be my fundamental, my n equals 1. And then I can ask myself, well, what's the next possible frequency for this particular string? Fixed strings are fairly straightforward as far as oscillators go. And there's my next one. And then I'll just draw one more, but we could go on forever with this. I'll just draw one more. There's my n equals 3. So the thing that I want you to envision here is that for the fundamental case, my n equals 1 case, there's one what I call loop, right? Some people count nodes. They'll say, well, they'll use some kind of algorithm with the number of nodes or antinodes, and you can certainly do that too. Like the fundamental case has one antinode, and the n equals 2 case has two antinodes. Antinodes is, of course, the maximum displacement from the string. So this is your antinode here. And then the n equals 2 has two antinodes, right? One here, one there. The n equals 3 has three antinodes. But I also like to just describe them as loops. So n equals 1 is one loop, n equals 2 is 2, n equals 3 is 3. I know this all seems really obvious, but the point here is that these are multiples of the fundamental. All the other possible frequencies are multiples of the fundamental frequency, right? This is useful. So if we're told that we have these two consecutive frequencies, 400 and 480, we can use those numbers to deduce that, guess what? I can figure out the fundamental frequency for the system then. It must be the difference between those two. So it must be 80 hertz. Okay. So I've got that, right? That fundamental frequency is 80 hertz. Cool. And again, it's really, really important that they told us that those were consecutive frequencies. If there were, unknown number of frequencies in between those two, then we would have to consider that the fundamental could be a smaller frequency. All right. So what's really important here is that I guess what they're asking us here, the wavelengths of the two resonant modes. I'm going to actually draw out the two modes. I think that's really important. So if we know that this is our fundamental, what that tells us, if we look at the 400 and 480, is that that's the fifth and sixth mode, right? So I could do all these multiples in here, 1, 2, 3, 4, 5. But I know that if I take 400 and divide it by 80, right, that's going to be the fifth mode, and 480 divided by 80, that's going to be the sixth mode. And again, it's fairly straightforward. These are just multiples of the fundamental frequency. So what will my fifth mode look like? Or my n equals 5. I can draw out the string, and it'll have 5 loops, right? Which I'm going to try to draw. 1, 2, 3, 4, 5. All right, now let's say the string has some length. Well, we know the string length is given as 4 meters. I'm just going to call it L right now. And then the other mode that we're told about is the n equals 6 mode. Again, I really encourage you to draw these guys if you can at all. So 1, 2, 3, 4, 5, 6. They don't have to be perfect, as you can see by my drawings, but it really helps your brain to, kind of grab on to what's going on with the situation. Pictures, our brains love pictures. So the fifth mode, if I look at this, I can see that the length of the string here is equal to how many loops do I have, right? There are different ways of doing this. So I could say 1, 2, 3, 4, 5. I have 5 loops. Each loop is 1/2 a wavelength. So L equals 5/2 of a wavelength. And I'm going to subscript that wavelength with a 5, showing that I'm in the fifth mode there. And for the n equals 6, L equals, now here I've got 6 loops, right? So I could say 6 over 2, lambda 6, which is just equal to 3 lambda 6. So right here, I've got my relationships between relating the length of the string and the wavelength. So we're on our way to answering part A then, right? So for part A, I can say that lambda 5 is equal to 2/5 L. And then if I sub in my 4 meters here, I'll get 1.6 meters as my numeric answer. Part B, oh no, I'm sorry, we're still on part A. Lambda 6 is equal to L over 3, which is going to be equal to 4/3 meters. Okay, so that's answering part A. I've got the wavelengths. And notice that especially for wavelengths, if you draw it out, it often becomes obvious. If you find yourself going in circles with the equations, then just stop and draw the pictures. And sometimes it is right in front of you. You can literally be counting the half wavelengths on the string. So definitely use the fact that these standing waves are really easy to visualize. Leverage that for yourself when you are solving these problems. Part B asks us for the tension in the string. So we remember how wave speed relates to tension, and then we can solve that for tension. Tension then equals mu times wave speed squared there. So we can use any mode that we want to here. This is just one string. So the wave speed, it only has one wave speed on it. So remember, this same string can have multiple wavelengths, multiple frequencies, but in order to change the wave speed, you'd have to change the medium itself, right? Wave speed depends on medium. In order to change the wave speed, you have to change something about the medium. And we're not doing that here. We're not changing the string tension. We're not changing the linear density. Nothing about the medium itself is changing. So there's only one wave speed. You can use any mode to solve for the wave speed. It really doesn't matter, right? Wave speed is just going to be the product of wavelength and frequency. You have to be really careful here, though. What I have seen students do is sometimes mix modes, like use the wavelength from the fundamental and the frequency from the fifth mode or something. You can't do that. It has to be consistent. So you have to use the wavelength and frequency from any particular mode. So for instance, I could use the fifth mode, say. I could use the fundamental too. I could use the sixth, but let me just use the fifth here. But I have to be consistent, right? So if I do that, that will look like the fifth mode wavelength, which is 1.6 meters, multiplied by the fifth mode frequency, which is 400 hertz. So that gives me 640 meters per second. Now I can solve for tension because remember that linear density is given. So tension is just going to be linear density, which is given to us as 6 times 10 to the negative 3 kilograms per meter, and multiply that by the square of the wave speed. So I get something like 2458 newtons for the tension.